Okay, yeah, it's recording.
Okay.
Okay.
So this is Andreas Prodromou, and he's going to be presenting his PhD dissertation, which is achieving accurate predictions of future events under hardware heterogeneity.
Thank you, Dean. Thank you all for being here. So yes, as Dean said, the title is Achieving Accurate Predictions Under Hardware Heterogeneity, and I'll just jump right in with a quick background. The way we execute modern software today, we typically run it on CPUs and GPUs. However, there are a few more options, such as field programmable gate arrays, FPGAs, and application-specific integrated circuits, ASICs. As we move to the right, the hardware becomes more and more optimized for a narrower and narrower set of tasks. Now, these heterogeneous execution engines, really, they can be combined in systems on chips, and they can be parts of larger data centers. The benefits of this type of heterogeneity include, well, we have highly optimized hardware for each task, which leads to improved performance, power consumption, bandwidth cost, and so on. On the downside, however, we have reduced flexibility. We are required to write accelerator-specific code, for example, CUDA to run on NVIDIA's GPU, which increases the difficulty of development and testing. And another problem is that when you do that, you hard code resource management. For example, if you write something in CUDA, then for the most part, it must run on a GPU, even if for whatever reason, it doesn't make a lot of sense to run on the GPU at a given time. There's a different kind of heterogeneity intra-processor, in which case we can have architectures like heterogeneous memory architectures, where we have high bandwidth, 3D stacked memory on chip, along with the traditionally used off-chip DRAM. We can also have heterogeneous multi-core architectures, in which case we can have big, high performance, high power consumption cores coexisting with smaller, lower performance, low power consumption. In this case, in this architecture, all these cores must implement the same instruction set architecture, or ISA, which is the low-level language that each core kind of understands or speaks. There's a third kind of heterogeneity currently at its research stages, which allows for the ISA to differ. It's called heterogeneous-ISA for architecture. We can still have cores of various sizes and specs, and we can also vary the ISA. The benefits of this is improved flexibility, because the same code, this is general purpose hardware, the same code runs on all available hardware, and it allows us to take resource management and do it dynamically. On the downside, we do not have as optimized hardware for a task as we would have with ASICs. So if it's not as optimized, then how do we get a benefit? We get a benefit because of the behavior of software. Software can have varied requirements, can be compute or memory bound. It can have various levels of parallelism, different memory access behavior. And there's also something called the ISA affinity. It's been shown that software has a preference in ISA. It will run faster on one ISA over the others. Just to give an example, we can have a compute-bound program on a big core where it's going to utilize all the available resources and run very fast. And at the same time, we can assign a memory-bound software on a small, low-performance core. Since this program is going to spend most of its time idle waiting for memory, then we don't really lose performance and we save on power consumption. Taking a look in the literature, we can see on the heterogeneous memory architecture side, we can see performance improvements up to 30%. Even the reliability of data itself improves by up to 1.5 times. On heterogeneous ISA multi-cores, we see 21% performance improvement, 23 energy, 32% reduction in energy delay product. And turns out, if we migrate software between ISAs, the researchers have shown that they can eliminate 99.7% of the opportunities for a particular kind of attack, a return-oriented programming attack. Now, these numbers look great, but there's a big assumption of excellent resource management in order to get there. To give an example, let's take a look at the scheduling problem. We have two cores, one big, one little, and we also have two programs. One's memory bound, the other is compute. And we want to, there's two possible ways to schedule. One is the correct way, where we gain in performance, power consumption, and we don't waste resources. If we do it incorrectly, however, we lose on all three fronts. So it is extremely important to have intelligent resource management if we'll be able to benefit from these architectures. There are, however, two significant challenges. The first one is we don't really know the requirements of software in advance. And the second is we can't really accurately model all the interactions between software and hardware with a simple formula. We need something a little more complex. Which brings us to the statement of this dissertation. If we achieve accurate predictions in the presence of heterogeneous hardware, we can improve resource management and scheduling, which in turn allows us to harvest the benefits of heterogeneity. During my research at UCSD, I've worked on heterogeneous memory architectures, both on the performance and reliability side, a few publications. I've also worked on heterogeneous multi-core architectures with our latest work currently under review at ASPLOS. And before I joined, I had some work on networks on chip. In today's presentation, we'll discuss MemPod, where we adopt a majority element algorithm, improves accuracy, and it's much cheaper. We'll also discuss machine learning-based performance predictors that we developed. And finally, neural net-based scheduler arbiters. We'll talk a lot more about all these. So let's begin with MemPod. The full title is this. And it's a memory manager for flat address space multi-level memories. Let's look at these terms. A multi-level memory is when we have two or more kinds of memory. In this work, we assume on-chip, 3D stacked, high bandwidth, limited capacity HBM, and lower bandwidth, higher capacity DRAM off-chip. The goal is to have the two memories work as one homogeneous high-performance memory. When we have a multi-level memory architecture, there are two ways to manage it. The first one is by using the HBM part as a high bandwidth last level cache. In which case the capacity of the HBM is not available to the software. The other approach, and the one we actually study in this paper, is flat address space, where everything is presented as a contiguous address space. It just happens that some data physically lies in the HBM region. The problem we're trying to solve has three steps. The first one is prediction. We want to predict pages that are about to be accessed, pages that will not be accessed. And once we do that, we want to physically swap the data, the migration step. And finally, a request comes in, and ideally, we want to serve it from the high bandwidth memory. We want to maximize the number of requests we serve that way. Let's take a look at prediction. And I'll start with an approach that was typically assumed in the literature, often assumed, called full counters, in which case, each memory page is assigned a counter. It increases by 1 on every access, which means this is a high memory overhead solution, and all these counters need to be stored in main memory. It's also an interval-based solution. It counts for a certain amount of time, and at the end of the interval, it predicts that the K pages, we can select whatever K we want. The K pages with the highest access count are predicted to be heavily accessed in the next interval. Now, this approach has a lot of challenges. The first one is we need to retrieve all the counters. And then we need to sort them, which we measured to take almost 2 seconds on a modern CPU. and intervals are proposed to be in the millisecond range, really. So high overhead, it scales poorly because larger memories, the larger it is, the more counters you need, and the more it worsens these parts. And finally, the initial assumption is not always desirable. Just because something got accessed heavily doesn't necessarily mean that it will be hot in the next interval. It doesn't balance sort of a fine-grained temporal locality. It doesn't favor things that were recently accessed.
So I have a question.
Yes.
So if instead of the, I still haven't seen your prediction model.
Mm-hmm.
That how forget about any sophisticated prediction model, but if you just use some sort of a bin count, like histogram-based prediction, how much you could advance this, whereas you're using kind of, I guess, the more fancy machine learning?
Okay, so for this work, we just use a heuristic, not machine learning yet. But to answer your question, there's various flavors of this approach in the literature. Researchers try out different granularities. So it might look a little bit like a coarser grain histogram. All decisions have their ups and downs. If you go larger granularity, then you kind of have to move more data, and you end up moving.
Yeah, I suppose you will be talking about that. But this counter and counts the dimension. Like this seems to be more like in count.
I mean, it is, yes.
Correlation, because machine learning is useful when you have a lot of correlation.
True. Yes. Well, there is software that has a more or less predictable memory access pattern. Some of that software could work with that. We don't use machine learning for this part. We instead use a count.
I'll let you talk because I talked to her.
No, it's but because of all these challenges, we wanted to do better. And the way we did is we adopted this majority element algorithm that was proposed in 2003 for database management. And what it does is it finds the k most frequently occurring elements in an array of elements, right? Which is exactly what we were trying to do with full counters. Now, this is a heuristic. It doesn't always guarantee a correct answer. However, it is formally guaranteed to provide the correct answer if this majority assumption holds, which for this presentation, it's not really important exactly what it is. What is important is that we cannot guarantee it. So we actually know that this algorithm will not work correctly. And where it gets interesting is that it is in the way it fails. Turns out when it fails, it kind of has a side effect that works really well. Before we get there, this is a streaming algorithm. So it touches each element once. There's no sorting overhead. We just save 2 seconds. It has a very simple implementation in hardware. It scales depending on how many elements you want to identify, not depending on your memory size. And when it fails, it balances access count and recency. So we'll see how this happens with a walkthrough of the algorithm. This is the algorithm on the right-hand side. On the top left, we have a walkthrough input, and we define k to be 3. We're looking for the 3 hottest elements. So we start by initializing the map, 3 entries. We read the next element. It is not in the map. The map is not full, so we add it with a count of 1. We read B and follow the same path. Then we read A again. This time it is in the map. We simply increase the count. I'll fast forward a little. So we're at this point, and then we read the next element, which is at D. In this case, the element is not in the map, and the map is full. What we do is we decrease all entries by 1 and remove the entries that are equal to 0. In this case, we don't remove anything yet. But when we read the next D, we do it again, and C gets evicted, and then E comes in, and the final answer is A, B, and E, which happens to be the correct answer because in this input, we satisfy the majority assumption. Let's see an example where it's not satisfied. This is the exact same problem. We just removed the last three elements. Running it, we get a wrong answer. But what happened here? So if you remember, at some point, C was heavily accessed, and it was in the map. The map got full, and then each new element was subtracting one from all entries. Inevitably, one of them, well, eventually one of them will become 0 and evicted. And when it does, it will be replaced by whatever element you access next, so the most recently accessed. And this is an example of how high count elements can be evicted in favor of something more recent. Now, this balancing of spatial and temporal locality is usually favorable in hardware. So we designed an experiment to compare the prediction accuracy of this algorithm and full counters. This is how our results look. On the x-axis, HG here means homogeneous workloads. We have 8 copies of the same benchmark running on 8 cores. We have mixed workloads where we have a random selection of benchmarks, and then we aggregate the results. As you can see, MEA achieves, on the y-axis we have the count, how many times a prediction was correct, was accessed in the next interval. And we only focus on the top 30 pages. But as you can see, the results are favorable. MEA seems to outperform full counters in terms of prediction accuracy. So we actually picked 5 benchmarks that are interesting. The first one, running 8 copies of Cactus on 8 cores, is the only case in our entire evaluation where full counters outperformed MEA. The following 2, Mix9 and Zalang, are more representative. This is what the majority of our results look like. And we have MEA outperforming full counters in all 3 groups. We grouped the 30 pages in beams of 10. And the last 2 are cases where full counters fail. It scored 0 hits. And the first one, we also failed. But in the second one, we actually got one of the highest scores in our entire methodology evaluation. And this is obviously because the particular benchmark has some sort of behavior that it's beneficial when we favor recency over access count. To conclude MEA, we've measured it to be significantly more accurate. And for the memory architecture assumed in this work, it actually takes almost 13,000 times fewer bits in memory to implement. Now, we paired this predictive approach with a microarchitectural proposal. I'll kind of go over it quickly. If there's any questions, please stop me. We start with a system. We have 8 on-chip memory channels, and then we have 4 off-chip. What we do is we cluster the channels in a 2-to-1 ratio. We hide the memory channels from the rest of the system. We create these memory pods which hold the entire logic for our proposal, and we expose the pods as memory channels. Now, in doing that, each pod only handles traffic for its member channels. Migrations only take place within clusters, which
I'm sorry, so this is the memory management, these pods happen in the memory management units? Like these are new entities that you define in the memory management unit?
This is what we propose, really. All the logic that we propose lies in there. So in doing that, each one controls migrations within its cluster, which also leads to reduced power consumption. And this is really a divide and conquer approach, which should scale better to future memories. On the downside, by doing this, we serialized accesses to 3 memory channels, which could have been done in parallel. So we have to design the pods to be as efficient as possible. When a request comes in at the pod, it first goes through activity tracking, which is a hardware implementation of MEA. And it also looks up a remap table to see whether or not this page has been migrated before, in which case we get a relay address. it gets re-encoded into the request, and then it goes to the right memory channel. So everything is transparent to the rest of the system. It doesn't need to, it's just a level of indirection that is hidden. MemPod is also an interval-based approach, where at the end of the interval, we get a migration signal. We stop traffic for a while to ensure atomic memory updates. And then the activity tracking unit starts producing tuples of hot and cold pages, which update the remap table. And then a migration unit takes care of physically moving the data. So this is the architecture briefly. And then we went ahead and compared the performance of MemPod against 3 state-of-the-art proposals of the time. Yellow is MemPod, light blue is the best case scenario where there's only an HBM memory with enough capacity to hold all data. On the y-axis, we measure main memory access time. So lower is better. And results are normalized to a 2-level memory without intelligent management. On average, we measure 19% improvement. And compared to the best state of the art, which would be THM, we're 9% better. We wanted to see how our mechanism and the others, how they behave on future memories. To model a future memory, we decided to accelerate both the on-chip and off-chip memory, but increase the speed differential between the two. So we assume that HBM technology will mature and the difference between the two memories will grow. So we made the DDR 1.5 times faster and HBM twice as fast. We measure MemPod to, well, it scales better than the other approaches, partly because of its divide and conquer design. It's 24% better against a 2-level memory without migrations, whereas the best case scenario would have been 40%. So with these results, we conclude the first chapter of this presentation, MemPod, and we can move on to machine learning-based performance predictors, if there's no questions. Okay, the title of this work is Deciphering Predictive Schedulers for Heterogeneous-ISA Multicore Architectures. And really, this study has been guided by 2 questions. The first one is, can we actually train machine learning models to learn all the interaction between arbitrary software and hardware? And if we can, could we design one global machine learning-based scheduler, to support any underlying hardware and any software that shows up? Just a reminder, the scheduling problem and why we need this, why we need good resource management. But also, in this work, we chose to work with heterogeneous ISA architectures, partly because it makes the problem we're trying to solve more difficult. And to demonstrate that, assume this heterogeneous ISA chip and a thread that has been profiled on some x86 in-order core. Let's assume it was profiled on that one. If I ask you to predict performance when that thread runs on the same core, this is an easy problem. Hardware is the same, software is the same, we should expect similar performance. If I ask you to predict performance, however, for a different core, maybe an out-of-order core of the same ISA, the problem becomes quite a lot more challenging, actually, because the changes in hardware, they don't affect all programs the same way. If, however, the software remains the same, right? We haven't recompiled it. If we go on an out-of-order core, which happens to be of a different ISA, however, we still have the impact of varied hardware, but also the thread no longer behaves the same. It runs on a different ISA. There could be a lot of changes in its dynamic behavior. So it makes the prediction problem we are addressing quite a lot more difficult. At a high level, in this work, we explore 3 machine learning models: ridge regression, a linear model, and 2 tree-based models. And we We also focus on imposing minimal human knowledge. We allow our models to explore the space our dataset provides. And we also designed our methodology to allow us to automatically extract the systems we should be testing our proposal on. In this work, we use the largest heterogeneous-ISA simulation-based dataset. Credit goes to Ashish Venkat, who created it. And it includes 72 applications, each one profiled on 600 cores, 43,200 entries. Each entry has 30 features that describe the dynamic behavior of a workload as it was profiled in simulations. This can be performance, instruction mix, its dynamic behavior, and so on. And we can also have 18 features that describe each core, which are, these are features available from the manufacturer. It can be things like which ISA we have, a description of functional units, cache architectures, and so on. Sorry, just a second. Okay, what we propose in this work is we start with our data set, we feed it into a machine learning performance predictor, which generates predictions for each workload for each core. We measure performance in alpha instructions per cycle, which is a metric we developed to ensure fair comparison between ISAs, fair comparison of progress between ISAs. Once we have all the performance predictions, we can pass that to a scheduler, which will come up with a job to core assignment. In this work, we focus on the left part, and in the next chapter, we'll discuss the actual scheduling. The first question we have is, do all systems, heterogeneous ISA multicore systems, require advanced and complex schedulers? It could be that there's a trade-off. Maybe we can sacrifice a bit of peak performance to ensure easier scheduling. And we wanted to quantify it if there is one. So we came up with a metric called ease of scheduling, or EOS. Basically, you give it a collection of cores and it gives you a number between 0 and 1 that says how easy it is to schedule for that multicore. The insight behind it is if you have easier systems, a random scheduler will perform better. So for this experiment, we randomly draw 7,500 multicore systems. On each one, we execute 200 workloads, appearing one at a time whenever another one is finished. Whenever a new workload appears, a random scheduler intervenes and creates shuffles workloads around. And eventually we compare that against the optimal scheduler.
So how many different types of cores do you have?
Well, our dataset has 600 cores to choose from, 200 for each ISA. And these are randomly drawn systems with the only rule that it's got to be heterogeneous ISA. There's one core at least from each of the 3 ISAs. Okay? Okay, so eventually, the closer random gets to optimal, the easier the system. Our results look like this. On the X core, we have the system's average performance, assuming optimal oracular scheduling. On the Y axis, we have the ratio of the random scheduler against the scheduler. The higher up we are, the easier the system. To give an example, this system is quite low performance, 0.5 alpha IPC per core on average. But the random schedulers can achieve 90% of the oracular scheduler's performance. Now, depending on the situation and the exact scenario, this 90% might be enough or it might not. But the point is, that system is significantly easier than, say, this one. We noticed that the number of cores has an impact with each cluster starting lower, and we also see significant diversity within the clusters. With these results, we pick 9 benchmark systems for this work. And the way we do it is, we pick the easiest, highest dot, the hardest, lowest dot, and median from each N. So this would be 3 examples. And these are all 9 of our systems. In doing that, we ensure that we cover efficiently a very wide range of underlying hardware, which would allow us to demonstrate the flexibility of our predictors. Before we get to results, there's a few details on the training aspect. The first one was a challenge in data splitting. This is what our data set looks like. We said there are 72 workloads, but these workloads are, in fact, profiled phases from spec 2006 benchmarks. If we follow the easy way, a 50-50 split between training and test sets, we have the following problem that maybe 2 phases from the same benchmark lie in different sets. And we've measured that to artificially boost our prediction accuracy. In fact, by putting a single phase in the training set and all other phases in the test set, we measured the prediction accuracy to improve by 3 times. So a better way to do it is a leave one group out logo approach, where an entire benchmark with all its phases profiled on all cores become the test set, and everything else goes in the training set. When we present results later, we assign each benchmark to be the test set once, and we report averages. We also wanted our models to freely explore the features our dataset provides. So we group them. For example, we can have all the cache-related features to be a group, or the instruction mix. And we also have 10 flags that turn them on or off, so they can hide a feature group from a model during training. And we follow a brute force approach. We train 1,024 models, and we pick the winner model from each of the 3 algorithms to be the one with the highest accuracy on average across groups. This is what our results look like. We measure accuracy in mean absolute error, which is in alpha IPC, and we also measure the standard deviation of error of each predictor. Over the test set, we see all 3 algorithms performing roughly in the same range, around 0.2 mean absolute error, which is pretty good considering that our alpha IPC in our data set ranges up to 4.5, and they also show 0.3 standard deviation. Over the training set, we see the linear model performing roughly in the same region as the test set, but the tree-based ones are more complex. They have more capacity to feed the training set. Now, we actually do care about prediction over the training set because we're designing schedulers, right? And a scheduler, a realistic one, first of all, we have to assume that it will be periodically retrained. And we can also assume that it will be phased with the same input, same program to schedule, maybe sometimes even the same input to the program. So we do want it to perform very well on previously seen data without, of course, sacrificing test set accuracy. So we train our models, we find the winner model from each algorithm, put them in a scheduler, and compare performance. Yes?
What's your unit for
mean absolute error, which is measured in alpha IPC. We're predicting performance. Okay. All right, so performance results. On the x-axis, we have the labels for the 9 benchmark systems. I should point out, this is one, we don't retrain predictors between systems. It's the same predictor from each algorithm. So the models we're working with, this is the performance of the system normalized to that of optimal scheduling. And finally, we compare 4 models. 3 of them are ours: random forest, decision tree, bridge regression. And this one is basically an error-free version. It oracularly knows the correct performance. It's greedy because it doesn't see the future. It doesn't know which workloads will show up, same as ours. So comparing the random forest against oracular, which I should point out is not realistic. We can't really have that in most cases. We lose 7.5% of performance on average across all systems. Decision trees, which are much cheaper than random forests, we lose 10% of performance. And we see the linear model failing to adapt to the increased difficulty of the underlying model. Now, we repeated the entire methodology. Everything I've presented, we redid it, but this time for single ISA heterogeneous multicore. So we don't have multiple ISAs, they're all alpha. Same results. By moving to single ISA systems, EOS rating went pretty high up. The single ISA systems are easier to schedule. And we can see this, our decision tree model only loses 4% of performance on average compared to Oracle. And the linear model becomes comparable to the tree-based models. With these results, we can conclude this chapter and move on to the last one, which is our latest work. Oh, we're good on time too. Are there any questions so far? Okay. This last work, we named it Agon, or Agon in Greek. It's a competitive scheduler for large heterogeneous systems. In the previous chapter, we focused on this part of the problem. But what happens there? Let's begin by taking a look at what that section does. It starts with a performance matrix, right? The scheduler's job is to find the row permutation of this matrix that maximizes the sum on the diagonal. Technically, that's what it does. The diagonal is a schedule. It's a workload-to-core assignment. And by maximizing the sum of performances, we maximize the overall performance of the system. Now, there is one algorithm besides brute force that can guarantee a correct answer. It's called the Hungarian algorithm. Its algorithmic complexity is cubic, and which makes it not efficient for very large numbers of cores. There are, however, faster heuristics that do not guarantee finding the best schedule. So we went in the literature, we found 6 different proposed heuristics for scheduling, and we compared their overhead as the number of cores grows. Note that the y-axis is in logarithmic scale. So as you can see, some approaches are very low overhead, like random, which will not produce a great schedule, and others can be quite expensive. Now the question becomes, if we have a higher overhead scheduler, does it guarantee better system performance? And the answer is not really. So we've identified 3 factors that impact this. The first 2 have to do with the heterogeneity level. One in the hardware side, so this is a modified EOS experiment. But the point is that some systems are just easy to schedule. So maybe for those systems, you don't need the full complexity of a high overhead scheduler. The same argument can be made on the software side. So what we have here is, ignore all these signs here, but those are 4 workloads being scheduled on 4 cores. The blue dots are all 24 possible schedules. And the point here is that the difference between the worst schedule and best schedule, they're quite close. And also there are 4 schedules that are basically optimal. So a random scheduler has 1 in 6 odds of working perfectly. So these 2 arguments make it so that maybe sometimes we don't need the full complexity of Hungarian. The third factor is, even if we run the Hungarian algorithm every time, it can't really guarantee a correct schedule, not because it doesn't work, it's fine, but the input we give it comes from a predictor which will unavoidably have some error. So we're feeding an algorithm with erroneous inputs, and we measured the prediction error to have an impact on system performance up to almost 10% for the Hungarian algorithm on 16 cores. So because of these 3 factors, there may be opportunities to save on some scheduling overhead. What we propose is a scheduling arbiter that, given the state of a system, it just selects 1 out of 6, in our case, choices, in a way that maximizes the net system performance, which is defined as the ratio of useful instructions over the total execution time, which includes the scheduling overhead. To give a toy example, we have two schedulers. A is high overhead, it generates a fast schedule. B is low overhead, generates a slower schedule. If you put everything together, it's scheduler B that improves net system performance. So let's take a look at what we propose. At a high level, a performance matrix runs through a neural net classifier, and the classes correspond to the scheduler that should be used. If we zoom in, we have, as expected, a backend classifier, but we also propose a front-end denoising module, which is, it's basically an autoencoder neural net. It works quite in the same way as image denoising. We assume that our 2D matrix is a grayscale image and prediction error is noise. So we try to run it through a denoiser, see what happens. We'll see results, but first let's take a look at the neural nets. We propose two approaches for the classifier. First one is just 3 fully connected layers. The sizes are for an 8-core system. From now on, we label this architecture as deep for the rest of this talk. We also propose a convolutional network with 1 layer of convolution and downsampling, followed by 3 fully connected layers. Again, here, if we assume the prediction, the performance matrix is a grayscale image, then maybe patterns in that image give us information about how relaxed we can be in choosing a scheduler. That was a concept, anyway. So moving on, this is a mistake with my animation, so let's start with that. The front-end denoiser, we also propose a convolutional architecture with convolution and downsampling, and then convolution and upsampling. And we also have the simple, fully connected layer autoencoder approach. Before we go ahead and look at the results of this, how these modules perform, we had to generate a few data sets for this work. To do that, we start by randomly drawing 1,000 multi-core systems, and we also draw 20,000 sets of n workloads to run on those systems. We combine the two to generate 20 million, basically these are instances of the scheduling problem, 20 million performance matrices. And finally, we do some math to compute which scheduler really should be used at each case. This leads to data sets for each n of 20 million entries with n times n features. So as I said, we generate 3 data sets. The first one, it really has to do with how we populate this matrix. The first one is optimal, oracular, sorry, where the values are error-free. They're just whatever simulations report. We mostly use this as a comparison point and for some bookkeeping. We also have a statistical data set where we model a performance predictor using a bell curve. We randomly draw error and we apply it on the oracular value. And finally, we have the realistic data set, which is the one we care to do well on. We call it multi-logo. And the predictions come from a trained decision tree predictor where we used 6 out of 10 benchmarks as a training set, with the remaining 4 being kept unseen. So with these data sets, we went ahead, we trained our models, and let's see some results. First, let's talk about the backend, trained individually. There is no front-end denoiser, it's just a classifier. On the x-axis, we have the 2 architectures we propose. On the y-axis, prediction accuracy, that's defined as the amount of time it actually predicted the correct answer out of 6. And the system labels, we selected our systems much in the same way as earlier, except this time we use the easiest, hardest, least, lowest performing, and highest performing. And we only focus on 8-core models. Finally, we have 3 bars, 1 for each data set. Let's start by comparing the realistic multi-logo versus the unrealistic oracular one. Prediction accuracy drops between 1 to 8%, but they're still, we can argue they're comparable in prediction accuracy. If we compare the convolutional architecture versus the deep one, on the oracular dataset, it improves accuracy by up to 7.1% and up to 10.4% on the multi-logo dataset. And finally, the hardest system scores 89%, while the rest of them are in lower levels. This is when we have just a classifier. So let's see what happens when we have just a denoiser. So we don't have a classification problem. We measure mean absolute error in alpha IPC. We have the 2 architectures we proposed and the 3 data sets. Let's focus on the blue one, on oracular. Mean absolute error is below 0.05 alpha IPC in all cases except 1, which tells us that this is in fact a solvable problem. It started with 64 elements, narrowed down to 32, but it kept enough information to recreate the input with low error. On the multi-logo dataset, I should define that in this case, we give in erroneous input and we ask it to produce oracular input. We ask it to remove prediction error. The mean absolute error we measure at the output is on average 0.11, whereas the predictor, the generator of the input, has a mean error of 0.25. So it actually drops prediction error. And on the statistical output, it grows a little to 0.14. So let's see what happens when we put the 2 together. So we have front and back ends linked. We train them as a single classifier. On the x-axis, we have the 2 classified architectures, and we have 1 bar for each front end architecture. We also have none. That's a case with just a classifier. Again, we measure prediction accuracy on the y-axis, and these results are just for the multi-logo dataset. First of all, the addition of a denoiser seems to improve accuracy on most systems. If we have a deep classifier, pairing it with a simple front end boosts accuracy up to 6.3%, 11% if we pair it with a convolutional one. If we have a convolutional backend, we actually measure that a simple front end doesn't help accuracy. It seems like the convolutional classifier has enough complexity to deal with prediction error. And adding a convolutional front end, this is the largest version of what we proposed, it improves accuracy up to 2.6%. If we take a look at what happens on the oracular dataset, things get a little interesting. Remember, this is error-free input, right? So on the blue bar, we can see what a classifier on its own does. It appears that when we add a denoiser, front-end denoiser, prediction accuracy goes up, which makes us think that the front end doesn't really work as a denoiser anymore. What it does is it takes in an input and it generates a new input with the goal of improving the classifier's accuracy. So it's more, there's a nice synergy between the 2. Okay, so now we pair up our decision tree predictor, put it in a, link it with the AGON scheduler arbiter, and we compare system performance. These are the results. With the green bars, we have the performance of, if you could oracularly pick the correct scheduler, that's the performance you get. All our results are normalized to that. We then have 6 yellow bars, which are we call them the always strategies. So, for example, that would be a system equipped with only a Hungarian algorithm. And we have the 6 options from the literature. And with blue bars, we have the 6 different versions of Agon. The label is frontend _ backend. Let's begin with the easiest 8-core system. We see Agon compared to the best always strategy, which happens to be Hungarian. It improves performance up to 4%. Compared to Oracle, we see a 5% performance reduction. The architectures with the convolutional front end, they seem to lose performance on this system, but on all other systems, all Agon versions perform better than everything else. Moving on to the hardest 8-core system, we see the Hungarian algorithm performing much better than the other yellow bars, and that is because of the difficulty of this system. But we also see all Agon versions outperform that one by up to 5%, and it's within 1% of Oracle. Next, lowest performing 8-core system. We do measure a performance improvement, but it's low enough that it makes it unnecessary to add all the complexity we need for Agon. Compared to Oracle, we get up to 99.9% of performance, whereas the always Hungarian approach goes up to 98.2. Finally, the highest performing system. Here we see Hungarian strategies failing. And because the system is such high performance, every cycle that is spent on scheduling costs a lot. You could have been executing a lot of instructions in this system. And that's why low overhead schedulers perform better. Agon is measured to range from 97.6 to 99.1% of Oracle, whereas the best always strategy, which would be always local, at 95.1. And with these results, we conclude this last chapter of the dissertation. We were able to improve heterogeneous memory architectures using MemPod. On heterogeneous multicores, our machine learning-based predictors improve system performance, and we can further improve performance by saving on scheduling overheads, which creates a nice combination of improvements. With that, I'd like to take the opportunity to thank my advisor, Dean Townsend, everybody who showed up, the committee members, and if you have any questions, I'll be glad to answer them. Thank you. That was 128 slides. But
Last chance for questions for Doug. All right. Go to Leon.
Do you want us to step out?
Yes.
I'll catch up with you soon. I've always been curious to see what happens in this part of the defense.
So I have a basic question when you're talking about getting like 90%. Do you feel like you got the low-hanging fruit and you have to do a lot more work to get the remaining 10%, or you could do more and get the 10%, or do you feel like you got kind of all the fruit, what's left is just sort of inherently unpredictable?
Okay, so I'll have to repeat the question for this. The question is whether or not, if I understand correctly, whether or not we should invest more time to finish the remaining 10% of prediction accuracy. Is that right?
Yeah. I mean, that's one way of phrasing it, sure.
Yeah.
Is it possible, or is it just?
Is it possible? It should be possible to get better accuracy than ours, because really we tried a few models and it seemed to work. However, I'm not sure if it's necessarily worth it, because you're selecting a scheduler, right? So even when you mispredict, you have something that's, besides the random ones, you have something that's designed to produce an okay schedule. And it doesn't mean that if you mispredict a scheduler, you get zero performance. So overall, and that's how we were able to get to 99% of what I call performance, while we had 90% of prediction accuracy. So at least for the systems we study, it's probably not worth investing more, unless you're going to come up with a nice new architecture or something more interesting.
So I have a question. So I guess there's a lot of work in industry that's going on with designing like memory management, like splitting things up. Like, how is this one getting transferred? Like, to technology? Are there companies that are, thinking this performance is so worthwhile, they're picking up your algorithm?
Well, okay, first I need to clarify that it's not my algorithm. I just adopted it for our.
No, I understand.
Yes.
But when I say my algorithm, I mean using whatever the Scott Schenker or whatever algorithm with your migration, which I got from the presentation, was your idea, and applying it to computer architecture, right? So how likely is this approach to, like, is this a super critical problem in industry? Like, are there a lot of people picking up your results and running with it?
Okay, so Ryan, the question is how the industry is responding to this proposal, whether or not it looks like it can be adopted.
I mean, there are two questions, but I mean, can it be adopted as is, but also how important it is for them to adopt it? Like, is it something that is stalling them from progressing?
Sure.
And they need this algorithm to go forward.
Sure. I don't understand all the business side of things, right? However, the MemPod work started during my internship at AMD, and it has been patented with them. So I take that as a sign that they're interested to eventually use it someday. While I was there, I did see a lot of interest in coming up with memory managers. And the numbers show significant benefits. The architectures already exist, AMD is producing. So I would say that yes, there is interest, and yes, they need to adopt something like this. I would suggest they adopt this particular one, but there's other options. The paper itself has been cited a few times over the years.
Is there any concern from these companies about using machine learning for these types of things? Like in some domains, there's a lot of concern about using a machine learned model that is not totally understood. Is that true here, or is that it doesn't really matter because you're getting a functionally correct result?
Well, that's a good point. The functionally correct result is a good point, but I've seen this. There is this concern that, especially in designing hardware, that we want to understand why things happen, and sometimes it's not very clear, especially with neural nets. That's why part of in the second chapter of the work, I didn't present it, but there was a lot of focus in understanding what those machine learning models learn. And that's why we actually chose those particular models instead of something more complex.
You do some error analysis on the neural network models in terms of which cases they got wrong and which ones they got right, and
I did not really, because we generated millions of instances. I guess it didn't. It's a good question. It didn't cross my mind. What I did see, though, something that I thought was interesting, the denoiser front end. So you pass in an erroneous input, and it tries to output an oracular one. I noticed that in the majority of cases, the elements that change, in the vast majority of cases, they move towards the right direction. They get increased or decreased correctly, and sometimes the amplitude is not all the way there, but the direction was correct. I just thought that was interesting.
So do you think that, your results are on smaller number of cores, right? Something like 16 or that range. Does it make sense for this technique to scale up to a larger number of cores? And how do you think it would work if it actually made sense?
There's a few things there. I think it would make sense to scale to larger cores, because as you scale, it becomes more and more important to do correct scheduling, and you can save a lot more in scheduling overheads. Now, the reason we focused on 8-core chips here is because it shows a decent distribution of which scheduler should be used at any given time. Whereas if you're at a 4-core system, almost all answers are the Hungarian algorithm, because it's only 4 cores. And as you go to 16 and more cores, then the Hungarian option kind of disappears because it's way too expensive. So the reason we focused on 8-core is to show the full distribution of schedulers. But there is enough variation on which scheduler should be used on larger chips. We only studied up to 16, but there's still enough good options to merit some sort of intelligent arbiter.
So my understanding is that your schedule is actually working online, right?
Yes.
So and you talked about this difficulty of scheduling versus the time it takes to make a decision in the online phase. But what if we do or you do, I do some offline, pre-training that helps, and then kind of use the simplified approach to do it in that.
That's a good question. So you could actually theoretically, right, take our data set or take some data set and train some predictor that is modeling the interaction between software and hardware well enough. And then as you take that pre-trained predictor, you put it in a real system, and then as you retrain based on that system's requirements, you basically start off at a better point.
Yeah.
It is possible, yes, we could do that.
No, but the question, you haven't evaluated
that. Well,
most of your training, if not all, is offline. Right?
Yes, so the actual study that we did is mostly offline because we just have a data set and we utilize that. But the assumption is that this will be moved online.
Yeah, the assumption is you're just using everything online that you're using it. But what if you actually did learn some stuff offline and started, instead of starting from a random point, start from more educated?
Well, I see. We didn't study that specifically because our training was basically what you described. It was the offline part, and then it's assumed to be used dynamically.
Because some of this recent trends, for example, they try to do reinforcement learning, try to have like some sort of pre-learned policy and then move on. They may be actually useful here.
Yeah, and I mean, as far as I know, there's success with that in neural nets, right? You kind of retrain the last levels and keep everything else warmed up. So I think it's roughly the same. It should be beneficial, I think. Any other questions?
All right.
Stepping out. All right.
It's probably the point where we should turn the recording of your.
Oh yeah.
Yeah.
How was that nice? Okay, let's hold on. Let me figure this.
Yeah. that without cutting Ryan off.
Yeah, this is, how do I stop recording? Oh, I need to stop sharing. Okay, just give me a sec. Stop sharing. And stopping